The examples in this video go with lesson 6.4, harmonic motion. Example 1, suppose that a block at the end of a spring is originally pulled 6 inches below the equilibrium position. After release, the block makes one complete up and down cycle in 0.25 seconds. Part A, what is the period of the motion? Well, conveniently, they've told us what the period is right here. That's going to be the time it takes to complete one up and down and cycle. So in our case, the period is going to be 0.25 seconds. Part B, what is the frequency of the motion? Well, our definition for frequency back here on this slide, the frequency is 1 divided by the period. All right, so let's take a look at this. The frequency is going to be 1 divided by the period, which we know to be 0.025. And when we put that in the calculator, we get 4. And these are to be measured. Let's see, it says cycles per unit of time. And our units are going to be in hertz. Okay. And this is in the textbook with the example that they did, and it is in section 6.4, which is on page 668 in your textbook. Okay, part C, what is the amplitude? Remember, the amplitude for a sine or cosine curve is just the height. And again, conveniently, this is given to us to be right here. Now, this is also important. So this thing is pulled 6 inches below, so that means its starting point is actually 6 inches from its resting point underneath it. Okay, so our amplitude is going to be the absolute value of -6, which is going to give me a +6 here. The -6 is here, the negative part is here because it's been pulled below the resting point. And then we take the absolute value of it to make sure our amplitude is always a positive number. Okay, part D, write a function of the form d is equal to a times the cosine of omega times t to model the displacement in inches of the block as a function of the time in seconds after the release. Well, conveniently, we know what this is. That was in part C. And we need to figure out the omega. So let's back up and see what our formula is to find omega. And it turns out we can use the frequency to find omega right here. We can say the frequency is equal to omega divided by 2 pi. Or we can use this formula right here, that omega is equal to 2 pi times the frequency. We can get that just by cross multiplying this formula right here. So let's do that. Let's find out what omega is. Omega is going to be 2 pi times the frequency, which we found to be 4 hertz. And that's going to give me 8 pi. And so when I write my model, and I'm actually going to do this on another page so we can see it, we're going to have d is equal to a, and we're going to put the negative in there, remember, because the starting point is going to be below the resting point of our problem, of our block. All right, so we have a times the cosine of omega, which we just found to be 8 pi, times t. And there's our model. And then for part E, it says find the position of the block 6.25 seconds after release. In other words, we're going to try and solve for D if we know that T is equal to 6.25. So let's go back to our model. And we're going to put in 6.25 for T. And we're going to find D. So D is going to be equal to -6 times the cosine of 8 pi times 6.25 And we're going to put this in the handy dandy calculator. Now, because this is written in terms of pi, that means we're in radians. So be sure you set your calculator to radians when you solve this problem. And when we put it into the calculator, we find out that d is going to be equal to -6. And our units, of course, we're going to be in inches. And so what this tells me is that 6.25 seconds after we have pulled the block down and let it go, 6.25 seconds later, it's going to have made some cycles, but at exactly 6.25 seconds, it's going to be back down at the bottom, 6 inches below the equilibrium point again. Example 2, a Ferris wheel is 120 feet in diameter with its lowest point 3 feet off the ground. Once all the passengers have been loaded, the wheel makes one full rotation counterclockwise in 1.25 minutes. Suppose that 2 children are seated at the lowest point on the wheel and are the last passengers to be loaded. Choose a coordinate system with the origin at ground level below the center of the wheel. All right, let's draw a picture here for just a second. We've got our Ferris wheel. This point right here is the lowest point on the Ferris wheel, and it is 3 feet off the ground. So that means the ground is going to be right here at this point. And if we draw in our XY axis right here, then the children are going to be seated at x equals 0 and y equals 3 at the lowest point on the wheel. And when they travel to the highest point on the wheel, they are going to be at 0 and 123. Because the Ferris wheel has a diameter of 120 plus that extra 3 feet that they are off the ground there. Okay. First thing we want to do is write a model representing the children's horizontal position in feet at time t minutes after the ride starts. Okay. So if the children are starting here at 0,3, a counterclockwise motion means they're going to be moving in this direction right here. And what that tells me is that the x coordinates are going to start at 0, and then they're going to move to the positive direction until they get to their highest point, and then they're going to start being negative until they get to the lowest point, and then they're going to start being positive again. Now, if we consider the graph of a sine function and the graph of a cosine function, this is best modeled by the sine function when we're trying to find the horizontal position. And the reason it is best modeled by the sine function is because you can see they're starting at 0, and once they leave 0, they're heading into the positive direction until they get to the highest point, and then they're going to start going in the negative direction until they get to the lowest point, and then they're going to start moving back up toward the positive direction again. Whereas if we tried to use the cosine, we're still starting at 0, but they're going into the negatives first until they get to the lowest point and then go back to the positives. So we're actually going to use the sine function to describe the horizontal position. Now I know that's a little bit counterintuitive because we said that sine goes with the y coordinate, cosine goes with the x coordinate. But we're going to do this backwards because of the way that the graph goes. The sine graph goes up first and then down, and the cosine curve goes down first and then up. And these guys in the Ferris wheel are going to be moving positive. That would be an upward direction on a graph before they start moving in a downward direction, which is negative. Okay. All right, so we know we're going to use the sine curve for this. So we're going to have our x coordinate is going to be equal to a times the sine of omega times t. All right, let's get the things that we need here. Okay, and we may want to go over to a blank slide here to do this. Okay, so x is equal to a times the sine of omega times t. All right, let's see the period. There we go, 1.25 minutes. Okay, so the period is 1.25. The frequency is 1 divided by the period, so 1 divided by 1.25. This gives me 0.8 hertz. The amplitude, all right, now let's go back and take a look at our picture. Now remember, we're talking about the horizontal movement right now, where these children are located. And so we're looking right here. They can be over here. This is the rightmost point that the children can travel. This is the leftmost point that the children can travel. And if we consider this point right here and this point right here on our number line, if this is x equals 0, this point right here is going to have to be positive 60, and this one's going to have to be negative 60, because remember, the diameter of this Ferris wheel is 120. So the furthest they can go from the center right here is 60 degrees to the right, or 60 feet to the right, or 60 feet to the left. So our amplitude is going to be 60 in this case. And we're going to use the positive 60 because the children are traveling upward first. Okay. All right. So all that's left is to figure out what omega is equal to. And we said earlier that omega was, oops, not that one. On this one, 2 pi times the frequency. Okay. In our case, we're looking at 2 pi times the frequency of 0.8, which we just found, and this is going to give me 1.6 pi. So it looks like the x-coordinate for the position of the children is going to be 60 times the sine of 1.6 pi times t. And this will give us the x-coordinate of where the children are going to be located t seconds after the ride starts moving. Part B, write a model representing the children's height in feet above ground level t minutes after the ride starts. All right, so the children, height-wise, are situated 3 feet off the ground. And when they're at their highest point, they're going to be 123 feet off the ground. So the amplitude is going to be half of the maximum 123 minus the minimum of 3. That's going to give me 60, okay? And we're actually going to be when we put this in our equation, we're going to put it in as a negative 60. And the reason we're going to put it in as negative 60 is because the children start at the lowest point on the graph, height-wise, okay? So we're not talking about the left-right movement. Now we're talking about the up and down movement, and they are actually starting at the lowest point on the Ferris wheel. So our amplitude, well, when we plug it into our formula, we're going to plug it in as negative 60 instead of positive 60. Okay, now, when the children start moving, okay, height-wise, we're at the lowest point. The height's going to increase until it gets to its highest point, and then it's going to start decreasing, okay? And so at the halfway point, as a matter of fact, it's going to be at its highest point, okay? Well, if we look at the sine curve, the halfway point is located right here. That's a 0, okay, or an x-intercept. If we look at our cosine curve, the halfway point is going to be right here. Now, this is the regular cosine curve, but we know this one's going to be inverted because we have the negative in here. And so if we look at the one that's been reflected across the x-axis, the cosine curve is going to look kind of like this right here. And so at the halfway point, it's going to be at the maximum point. And what that tells me is when we write our model for the height, we're actually going to use the cosine curve for that, okay? And so the y-coordinate is going to be a times the cosine of omega times t. Now, conveniently, we just figured out our a. We know what omega times t is because we just did that for the sine curve. But one other thing we have to take into consideration is that there is a vertical shift on here because height-wise, we're starting 3 feet off the ground. You got to be careful because the vertical shift is not going to be 3. All right, let's come over here. We know y is going to be equal to a times the cosine of omega times t plus some sort of a vertical shift. All right. The vertical shift is actually going to be halfway in between the lowest point and the highest point there. It's going to be their average, okay? All right, so our vertical shift is going to be half of our highest point plus our lowest point. So this is going to be half of 126, and that's going to be 63. So our y-coordinate is going to be negative 60 times the cosine of 1.6 pi times t plus 63. Part C, describe the children's position 2 minutes into the ride. In other words, when t is equal to 2, what is the x-coordinate and the y-coordinate for the children? Well, let's find out. All right. If t is equal to 2, then x is going to be equal to 60 times the sine of 1.6 pi times 2. Now when we put that into our handy dandy calculator, and I did that just a second ago, it gave me negative 35.3 feet. And then the y-coordinate will be negative 60 times the cosine of 1.6 times pi times 2 plus 63, and that gives me 111.5 feet, okay? So, after 2 minutes, the children are 35.3 feet left of the center and 111.5 feet above the ground. Example 3, suppose that 2 blocks of equal mass are attached to 2 horizontal springs and pulled 6 centimeters to the right of the natural rest positions of the springs and then oscillate at 0.25 Hertz. Due to internal friction in the springs and friction on the surface of movement, the blocks move in harmonic motion. The damping factor for the first spring is 0.4 and the damping factor for the second spring is 0.1. Write a function to model the displacement for each system t seconds after release. All right, let's back up a slide and look for the formulas that we want to use here. Okay, when we're looking at this damped harmonic motion, we're going to be using either this formula or this one, and it doesn't really matter, but when you consider the way that the spring is moving, we want to use the sine if the spring is starting in its resting position, and then if there's any displacement at all away from its resting position, we'll use the cosine curve. So for this problem, since we pulled that spring 6 centimeters to the right, that means there's been a displacement. We're going to use the cosine curve here. All right, so the one I'm going to use for my model is going to be D is equal to the amplitude A times E, and that is E, not the E, the variable, but this is E, the number, the negative, the 2.71828 number, okay, to the negative C times T power, and then C, that's just your dampening constant, okay, times the cosine of omega times T, and then remember we said omega was actually equal to 2 pi times the frequency. Now the frequency has conveniently been given to us right here as being 0.25. So our omega is going to be 2 pi times 0.25 or 0.50 pi. All right, A, our amplitude, this is going to be the absolute value of 6. It's positive 6 because we're pulling the thing to the right, and right is a positive direction. So this is just going to give me 6. And then I have 2 dampening constants here. All right, so for the first spring, my dampening constant is 0.4. For my second spring, my dampening constant is 0.1. So I am going to label these as D1 and D2. So the first spring and then the second spring. Okay, so D1 is going to be 6 times the cosine of negative 0.4 T times 0.50 pi times T. And then D2, the formula is going to be exactly the same, except the dampening constant is going to change. Now we've got negative 0.1. Oh, those should be E's there. Hang on a second. I'm sorry. All right, let's try this again. All right, so A is going to be 6. Then we're going to have E to the negative 0.4 T times the cosine of 0.50 pi times T. All right, that's our D1. D2, it's going to have the same amplitude times E. This time our dampening constant is going to be 0.1 times T. And then we're still going to have the cosine of 0.5 pi times T. And here are my 2 models to describe the displacement for each one of those springs.